Hi everyone, welcome to lecture 12 of solitons. Let me remind you that last time we started constructing new conservation laws for the KdV equation, in addition to the conservation of mass, energy, and momentum that, as I mentioned, are not unexpected. So I told you that in 1968, Gardner, Kruskal, and Mura were able to construct about 8 more conserved charges, which are not at all obvious that solutions of the KdV equation preserve. And the question that we wanted to answer next was whether there are, in fact, infinitely many more conserved charges, and if there is a systematic way to find them. And the method that, the answer is yes, and the method that allows to find this infinitely many conserved charges is the Gardner transform, which I introduced at the end of the last lecture. So what we saw is that the Gardner transform is equation 4.35. So we start from a KdV field U, and we rewrite it in terms of a new field W of x and t and its spatial derivative, as in equation 4.35. And then one can show, and I left it as an exercise for you to do, that the KdV equation for the field U is equivalent to the partial differential equation 4.36. So that takes the form of a linear differential operator, 1 plus epsilon partial derivative with respect to x, plus 2 epsilon squared w. Later on, we'll call that differential operator A. And this acts on an expression that depends on w and its derivatives. Later on, we'll call this expression z. And that's wt minus 6 times w plus epsilon squared w squared, which multiplies wx plus wxxx. When all of that is equal to 0, that's equivalent to the KdV equation for U. And in particular, we saw that it follows immediately that any W that solves the equation, which is obtained by setting the quantity in square brackets in equation 4.36 to 0, then also that's equation 4.37. So that automatically solves 4.36 because the differential operator A is linear. And therefore, given a W that solves equation 4.37, we can use the Gardner transform 4.35 to produce a field U that solves the KdV equation. So what we're going to see next is how to use this idea to generate conservation laws for the KdV equation. So I'm going to go to full screen now. To proceed, we're going to think about all of this construction backwards. Namely, we take the field U, a fixed solution of the KdV equation, and think of the new field W as something that varies with epsilon, the parameter that we introduce in the Gardner transform and in equation 4.36, in such a way that the Gardner transform 4.35 holds. So if epsilon is equal to 0, then equation 4.36, the equation for W, which is equivalent to the KdV equation for U, is nothing but the KdV equation with the reverse middle term. Namely Wt minus 6 WWX plus WXXX. equal to 0. And indeed, if we look at the Gardner transform, we find that when epsilon is equal to 0, u is simply equal to minus w. When you substitute that in a KdV equation, we get the KdV equation with the reverse middle term. On the other hand, if epsilon is not equal to 0, then we encounter two problems. The first problem is that to obtain w in terms of u, we need to solve a differential equation, which is the Gardner transform 4.35. And the second problem is that the differential operator, which I called A in 4.36, is now non-trivial if epsilon is different from 0. When epsilon was equal to 0, that operator was just the identity operator, but now it's a non-trivial operator. A, which is equal to identity operator plus epsilon partial derivative with respect to x plus 2 epsilon squared w in equation 4.36. It's a non-trivial operator, which in particular could have a non-vanishing kernel. And so we cannot immediately conclude that equation 4.37 holds. What we know is that the equation 4.36 holds, and that while equation 4.37 implies equation 4.36, the opposite implication is not true if the operator A has a non-trivial kernel. But now we're going to solve both problems at once. By viewing the new field W as a formal power series in epsilon. So W, if U is fixed, will depend on the parameter epsilon, and we view it as a formal power series, which means that we don't worry about convergence of the series. So in practice, what this means is that the field W, which is a function of x and t, is written as a formal power series sum from n to 0, from 0 to infinity, Wn of x comma t times epsilon to the power n, which is W naught, function of x and t, plus epsilon W1, function of x t, plus epsilon squared W2 of x and t, etc. This is equation 4.38. Now, to solve the first problem, namely that to obtain W in terms of U, we needed to solve a differential equation, which was the Gardner transform. Let's just substitute this formal power series expansion in the Gardner transform equation 4.35. And let's invert it order by order in epsilon. So I remind you that the Gardner transform said that u was equal to minus w, that's minus w naught plus epsilon w1 plus epsilon squared w2 plus higher order terms, minus epsilon times wx, so that's w naught comma x plus epsilon w1 comma x plus epsilon squared w2 comma x, etc., all differentiated with respect to x, minus epsilon squared w squared, so that's w naught plus epsilon w1 plus epsilon squared w2 plus dot dot dot, all squared. And now we're gonna expand the right-hand side and collect terms of the same order in epsilon. So first of all, the only term which is over the epsilon to the 0 is minus w naught coming from the first term. Next, let's write down all the first few terms in the first bracket. So that would be minus epsilon w1 minus epsilon squared w2 minus epsilon cubed w3, and then I'll stop. The second term, which involved the x derivative, came with the power of epsilon in front, so that gives us minus epsilon w naught comma x minus epsilon squared w1 comma x minus epsilon cubed w2 comma x plus terms of higher order in epsilon. And finally, the last term in the Gardner transform comes with an epsilon squared in front. And so we'll get minus epsilon squared w naught squared. And then at order epsilon cubed, we get the cross term between w naught and epsilon w1. So that gives us minus 2 epsilon cubed w naught w1. And then there will be higher order in epsilon that in principle we can calculate them. Okay, that was a substitution in the Gardner transform. Now let's invert order by order in epsilon. The first thing to notice is that u is fixed. So since u is fixed, we'll treat it as being of order epsilon to the 0. And so if we compare now left-hand side and right-hand side, order by order in this formal power series expansion in epsilon, so the left-hand side only has a term of order epsilon to the 0, so we'll start there. At order epsilon to the 0, we need to compare u on the left-hand side and the first column on the right-hand side. So we find that w naught is equal to minus u. At order epsilon, or epsilon to the power 1, there is nothing on the left-hand side. And on the right-hand side, we look at the first column. Since the sum of the two terms in the second column has to vanish in order for the order epsilon to the 1 term in this expansion to vanish, we obtain that w1 is equal to minus w naught partial derivative with respect to x. But w naught was equal to minus u, and so this is nothing but ux. Next, we move on to order epsilon squared. Again, there is nothing on the left-hand side. And on the right-hand side, we need to look at the third column. So that tells us that W2 is equal to minus W1 comma X minus W0 squared. And when we insert the expression for W0 and W1 that we just found, we see that this is minus UXX from the first term and minus U squared from the second term. Finally, we have order epsilon cube. Again, there's nothing on the left-hand side, and so we'll have to set to 0 the sum of the terms in the fourth column on the right-hand side, which implies that W3 is equal to minus W2 partial derivative with respect to X minus 2 W0 W1. And when we insert the previous expression and do a little bit of algebra, we found that this is equal to UXXX plus 4UUX. This 4UUX comes from a 2UUX, which arises from the first term in the left-hand side, and from another 2UUX arising from the second term in the left-hand side. And in principle, we can continue this procedure and determine all the coefficients in the formal power series of W as a power series in epsilon in equation 4.38 in terms of the KdV field U and its spatial derivatives. So we have managed to determine W as a function in terms of U, essentially without solving a differential equation, but rather by working order by order in this formal power series in epsilon. Next, we want to address the second problem, that the differential operator A, which appeared in equation 4.36, in principle is non-trivial, so it might have a non-vanishing kernel, and so we cannot conclude that the quantity in brackets in 4.36, which we call Z, vanishes, so we cannot conclude that equation 4.37 holds. But since W is a formal power series in epsilon, the same is true of the quantity I called X in equation 4.36, so the expression in the square brackets. So let's write down the formal power series expansion for Z. And similarly, in a minute, we'll do the same for the linear differential operator A, which acts on Z in equation 4.36. So to solve problem 2, we note that since W is a formal power series in epsilon, so is Z, which was the quantity inside the square bracket in equation 4.36 that I just showed you. So let me remind you that that quantity was Wt minus 6 W plus epsilon squared W squared times Wx plus Wxxx. That is what I call Z. Again, it's a function of X and T. And now we write it as a formal power series, sum n from 0 to infinity, Zn times epsilon to the n. Z is really a function, Zn are functions of X and T, and so we'll expand this as Z0. Again, it's a function of X and T. I'm omitting this from the notation, plus epsilon Z1 plus epsilon squared Z2 plus epsilon cube Z3 plus higher order terms. And similarly, we can do the same for the differential operator, which I called A. That was the identity operator plus epsilon partial derivative with respect to X plus 2 epsilon squared times W. I call that operator A. And we write this as a formal power series in epsilon. But first, let's notice that the zeroth order term is just the identity operator. So I'll write that out in front, and then we'll have a series sum n from 1 to infinity a n epsilon to the n, where the important point here is that a is a linear differential operator, and here boldface 1 is the identity operator. So in practice, by comparing left-hand side and right-hand side, we can see that a1 is nothing but a partial derivative with respect to x, which is indeed a linear differential operator. A2 is a linear operator which multiplies by twice w naught. A3 is a linear operator which multiplies by twice w1, and so on and so forth. So this is A2, A3, etc. are not really differential operators. They don't involve any derivatives, but they're simply operators which act by multiplication by an appropriate function. Later on in this course, you will call operators of this type multiplicative operators. Good, now we can go back to equation 4.36, which was equivalent to the KdV equation for U. And equation 4.36 took the form of the differential operator A, linear differential operator A acting on Z is equal to 0. And that takes the following form when we write it as a formal power series in epsilon. So we have 0 equal to, first I'll write A. I remind you that's identity operator plus sum n from 1 to infinity a n epsilon to the n, and that acts on Z, which we write as sum, say k from 0 to infinity Z k epsilon to the k, where I remind you zk are functions of x and t, and an are appropriate differential or multiplicative operators, which I just wrote. But we don't need to worry at this stage about what an and zk are. So let's just expand this out in a formal power series in epsilon and collect terms of the same order in epsilon. So first I'll act with the identity operator on Z, and I get Z naught plus epsilon Z1 plus epsilon squared Z2 plus epsilon Q Z3 plus higher orders in epsilon. Then I can act with the A1 which multiplies epsilon on Z, and so I'll get plus epsilon A1 acting on Z naught plus epsilon squared A1 acting on Z1 plus epsilon cube A1 acting on Z2 plus higher orders in epsilon. So next I can act with A2 epsilon squared on Z. So I'll get plus epsilon squared A2 acting on Z naught plus epsilon cube A2 acting on Z1 plus higher orders in epsilon. And finally, since we stop at order epsilon cube, I'll have to consider A3 times epsilon cube acting on Z, and in that case, we only need to worry about the terms of order epsilon to the 0 in the formal power series expansion of Z. So we get epsilon cube A3 acting on Z naught plus higher orders in epsilon, and then again we'll have even more terms with higher orders in epsilon from the higher order terms in the expansion in the formal power series expansion of A. But let's not worry about them. And now again we compare left-hand side and right-hand side order by order in epsilon. So now it's even easier because the left-hand side is 0. So at order epsilon to the 0, we need to worry about the first column in the right-hand side. So we conclude that Z naught must be equal to 0. At order epsilon to the 1, we need to set to 0 all the sum of all terms in the second column in the right-hand side. And so we find that Z1 must be equal to minus A1 Z naught. But Z naught, we just found that it must vanish, and A1 is a linear differential operator, so A1 acting on 0 is equal to 0. Next, we move on to order epsilon squared. So we look at the sum of all terms in the third column on the right-hand side. That has to vanish, and so that determines Z2 to be equal to minus A1 Z1 minus A2 Z0. But again, we just found that Z0 and Z1 vanish. A1 and A2 are linear operators, and so the right-hand side vanishes. So we conclude that Z2 vanishes as well. Finally, let's look at order epsilon cube. That's the fourth column on the right-hand side, which must add up to 0. And we can solve for Z3, which then must be equal to minus A1 Z2 minus A2 Z1 minus A3 Z0. We just found that Z0, Z1, Z2 vanish. A1, A2, and A3 are linear operators, and so the right-hand side vanishes again. So we find that Z3 also vanishes. And it's easy to convince yourself that if we continue to higher orders in epsilon, you'll find that all the coefficients Zk in the formal power series expansion of Z in powers of epsilon must vanish. This is equation 4.40. So the conclusion is that order by order in the formal power series in epsilon equation 4.37, which was nothing but Z equal to 0, holds. Let me remind you what equation 4.37 was. We started from the fact that the KdV equation for U was equal to equation 4.36 in terms of the new KdV field W. And we also had equation 4.37, that's what I call Z, the quantity in the square bracket in equation 4.36. So if equation 4.37 holds, then equation 4.36 holds as well, because A is a linear operator and Z vanishes. But we had the second problem that it wasn't clear that the converse would hold, because the linear operator A could have a non-vanishing kernel. And now we found that actually order by order in this formal power series in epsilon equation 4.36 implies equation 4.37. And the intuition there is that for small epsilon, the operator A is very close to the identity operator, and therefore it's invertible. And if when A is invertible, we can conclude that Z is equal to 0, and that's equation 4.37. Good. So we see that by using this formal power series expansion in epsilon, we can rewrite the KdV equation for U as equation 4.37 in W rather than a more complicated equation 4.36. And now this is useful because equation 4.37 takes the form of a continuity equation. So equation 4.37 can be rewritten as which I've just copied and pasted for convenience, is a continuity equation. Indeed, we can rewrite it as partial derivative of W with respect to T plus partial derivative with respect to X of minus 3W squared minus 2 epsilon squared W cubed plus WXX equal to 0. That's equation 4.41. And here we can identify W as the conserved charge density rho, and the quantity inside the square bracket as the associated current density J. And since W and all its special derivatives tend to 0 as X goes to plus or minus infinity, order by order in epsilon, that follows from the fact that W and its special derivatives were linear functions of U, Ux, Uxx, etc. Sorry, not necessarily linear, but were functions of U, Ux, Uxx, etc., which vanish at infinity, and that implies that W and all its derivatives vanish at infinity. So in particular, J, the current density vanishes at infinity. So not only we have the continuity equation, but we also obey the limiting condition, and therefore the charge Qtilde, which we define as the integral over space of the charge density rho, which is equal to W in this case, is conserved. That's equation 4.42. Good. Qtilde is a conserved charge. But now notice that since W, which is integrated, was a formal power series in epsilon, then so does the conserved charge Qtilde. And so in particular, we can write Qtilde, which is equal to integral over X of W, which was formal power series sum from 0 to infinity, Wn epsilon to the n. Now we can swap the order of integration and summation. If you're careful, you can only do that assuming sufficient convergence, for instance, absolute convergence. But remember, we're working with the formal power series, so we don't need to worry about convergence. So we just get sum n from 0 to infinity, epsilon to the n, integral over x from minus infinity to plus infinity, of Wn, the nth coefficient in this formal power series expansion of W, and that defines for us the formal power series expansion of Q tilde. So that's some n from 0 to infinity, epsilon to the n, Q tilde n. And now, since epsilon is a free parameter, and Q tilde is conserved regardless of the value of epsilon, it must be the case that the charges Q tilde n defined as the coefficient of this formal power series, so integral over space of Wn, the nth coefficient of the formal power series expansion of W, are all separately conserved. This is a question 4.43. So to summarize, by using this trick of the Gardner transform, which introduces a free parameter epsilon, and by thinking of the new field W as a formal power series in epsilon, and therefore all the expressions that depend on W, including the conserved charge Q tilde, should be viewed as formal power series expansions in epsilon, we found that there are infinitely many charges given by equation 4.43, which are separately conserved. Now we can go back to equation 4.39, which inverted the relation between U and W, so it allowed us to write all the coefficients Wn in terms of U and its special derivatives. Looking at those expressions and plugging them in equation 4.43 for the associated conserved charges, we find the following. So first we have Q tilde naught. That's the integral over a space of W naught, which was equal to minus U. This is nothing but the negative of the first conserved charge, which of the KdV equation, which is proportional to the mass. Next, we can look at Q tilde 1. That's the integral over x of W1, but W1 was equal to Ux. So this is the integral of a total derivative. So we get the difference of the limiting values of U at plus and minus infinity. And since the boundary conditions impose that U tends to 0 at plus or minus infinity, this is equal to 0. The important point here is that the integrand was a total derivative. Next, we look at Q tilde 2. That was the integral over x of W2, which is equal to minus Uxx plus U squared. The first term is again a total derivative, and since Ux tends to 0 at infinity, the corresponding integral vanishes. And so we're left with minus integral over x, minus plus infinity, of U squared. And this is nothing but the negative of the second conserved charge of the KdV equation that we interpreted as the horizontal momentum of the wave. Next, we can go on up to Qtilde 3 because we expanded up to third order in epsilon. So that's integral over x of W3, which was equal to uxxx plus 4ux. But now both terms here are total derivatives of say uxx and 2u squared. And by the boundary conditions, the boundary term vanishes, and so we get that Qtilde3 vanishes. And so on and so forth. In principle, we could continue to higher and higher order in epsilon to find more and more conserved charges. 4.44. As you can probably guess, there is a general pattern if you're interested in a proof of this general pattern. Please look at the book by Drazen and Johnson. But the general pattern that you can probably identify in equation 4.44 is that the Qtilde charges with the odd index to n minus 1, here n is an integer. So the odd Qtilde charges, they're all integrals of total derivatives in x. And so they vanish upon integration because all the boundary terms vanish thanks to the boundary conditions. On the other hand, the even charges, Qtilde 2n minus 2, do not vanish, but they can be shown to be equal to a constant times say, the nth non-trivial conserved charge of the KdV equation found using the method of Gardner, Kruskal, and Mura, so found by hand. So I remind you that the Qn was an integral which starts with the u to the nth power plus other terms. So these are the non-trivial charges, whereas the odd ones are trivial. So to summarize, we find that there exist infinitely many conserved charges for the KdV equation. And this is the key to the KdV equation being integrable. This is a property that you'll study in more detail towards the end of the second term. And as you see, when you look at the exercises in the problem sheet, in particular, exercise 23 and 25 in the problem sheet, we might discuss one of them in the next problems class. The presence of these infinitely many conserved charges places a lot of restrictions on the behavior of multi-soliton solutions, and in particular we can already extract quite a lot of information just by using these conservation laws. So that takes us to the end of this chapter on conservation laws, and what we'll start studying next week is instead the so-called Backlund transform, which is a method that will allow us to construct these multi-soliton solutions explicitly. So see you next week.